thanks a lot for inviting me to this Kuenen's webinar. It's a great pleasure and honor to talk about this urban emission monitoring and giving a general overview of current options presentation. So I think I'll dive right into the material. So what options do we have basically to monitor emissions in a city? We can do that using bottom-up methods or top-down methods. And I'd like to explain these terms here a little bit because different communities have different understandings of these terms. And I'm using the kind of the definitions that are typically used in the atmospheric science community. So we have here this nice figure from the Verify project, which kind of illustrates the differences between these bottom-up and top-down methods. Bottom-up methods are more these traditional methods where emission inventories are set up based on statistical data about the sources, their activities, and emission factors. So you collect information about what sources do you have in a city, in a country, how active they are, when are industries operating, how many cows there are that emit methane, for instance. And then you collect all this information, put it together, sum up to a country level, and then put it into a report, which is then reported to UNFCCC using IPCC guidelines on emission factors and so on. So that's what we call the bottom-up approach. Conversely, we have the top-down method, which works very differently because here we take atmospheric observations collected from ground-based stations or from satellite observations and combine this information with atmospheric transport models and inverse methods to estimate emissions. So we try to estimate emissions that are consistent with atmospheric observations, concentration measurements in the atmosphere. We can often actually combine the two, so we try to make the best out of the bottom-up information and the top-down information in a Bayesian framework where we optimize the emissions in such a way that they best fit both the atmospheric observations and the a priori information from the bottom-up. There was already quite many years ago a nice science article, a perspective article from Ewan Nisbet and Ray Weiss, emphasizing the need for top-down methods. And they phrased it in this way: greenhouse gas emissions are currently quantified from statistical data, so that's the bottom-up method, without testing the results against the actual increases of these gases in the atmosphere, which would be the top-down methods. And they said that this is like dieting without weighing oneself. So we commit to reducing our emissions, but we don't really measure the success of that using independent information. That's what top-down methods can bring. Now, why should cities be interested in applying these methods? So first of all, cities have a large share of global CO2 emissions and greenhouse gas emissions as a whole. There's many articles saying that's about 2/3 of global emissions are due to activities in the cities. Not all these emissions occur in the cities, but it's also electricity consumed in cities, which is then maybe produced outside of the cities. But it's clear cities have a large handle. Cities have set, next to nations, they have set often ambitious goals to reduce greenhouse gas emissions. For example, the city of Zurich has aims for carbon neutrality by 2040. And it's clear if these cities want to measure the success of their policies, they need reliable and timely data that inform on the pathways that they're taking. So for cities to monitor greenhouse gas emissions is usually the first step is to develop a bottom-up emission inventory of the current greenhouse gas emissions, or if we're talking about air pollutants, it would be an inventory of air pollutant emissions of a city, because you need to know what kind of sources are there in the city, and especially which are the dominant sources, because if you devise some policy measures, you want to address those dominant sources. And then you can define your measures, and they should be cost efficient to reduce the emissions. And now in the second step, we need to monitor the success of these policy measures. And where I see the top-down methods is twofold. On one hand, they help verify the bottom-up inventories by providing an independent observation-based estimate. And the second thing is, as you define your policy measures and try to reduce emissions in a city, they help track the efficiency of these measures, whether you're really on track. And they can do that basically in near real time, because atmospheric observations can inform these methods in near real time. And here's a nice result from a study that had been performed by Kevin Gurney and colleagues in the US. They looked at bottom-up emission inventories that have been produced by 48 cities in the US. And they compared these city inventories with a uniform Vulcan CO2 emission product. So that's a method to estimate CO2 emissions across the US for all the cities in a uniform way. And this Vulcan project has actually been also compared already against atmospheric observations, especially of radiocarbon observations. So that's kind of a quality controlled inventory. And they found significant differences between the reported emissions and the Vulcan inventory. And you see here in this figure the relative differences of these inventories. So red meaning somewhere between 50 and 100% difference between the self-reported emission of the city and the Vulcan inventory. And overall, the cities underreported CO2 emissions by about 18%. And there was a large range with between minus 145 and plus 63. So clearly there's uncertainties in the bottom-up emission inventories, and top-down methods can potentially help improve that. So top-down methods are already quite established on a national scale. And here within Switzerland, for instance, we estimate methane and N2O emissions using a relatively small network of observation sites on an annual basis. And we report our top-down estimates of methane and N2O emissions in Switzerland to our environmental Ministry for the Environment. And our estimates are then published in an annex of the Swiss National Inventory report to UNFCCC. And here this figure shows that actually our top-down estimate, which is this orange curve, so that's our estimates based on atmospheric observations, they agree really nicely with the bottom-up estimates, which is this green line, that's the National Inventory reported values. So there's some scatter around, but you see that we agree with the bottom-up within the error bounds. It's not always like this, but in Switzerland, we have a very nice bottom-up inventory that we could show that it is indeed of high quality and consistent with atmospheric observations. On the urban scale, these methods are much more sparse, have been not so frequently applied, but the best example we have so far is Indianapolis. There was a large project, or is still ongoing, influx, where a lot of measurement infrastructure has been set up in Indianapolis and operated for more than 10 years by now. So it's the largest effort to quantify CO2 and methane emissions of a city so far. It's a nice case because Indianapolis is a fairly isolated city, relatively far away from other larger cities. And there's it's quite an arid region, not a lot of biospheric activity, so not a lot of CO2 uptake by the biosphere. In that city, they tested a lot of different approaches, and here you see maps of the measurement infrastructure. So here you see sites that measure both CO2 and methane. Then there's also some flask measurements of carbon monoxide to complement the measurements, and there's also some flux tower sites. These are these white spots here distributed over the city. It's not only these in situ measurements that have been performed, but there was also some remote sensing here with a TICON, so that's vertical column observations of greenhouse gases. But there have been also aircraft flights downwind of the city. You see here an example where the wind was blowing from the northwest, and then downwind of the city, the fluid transects to measure the plume, the outflow of the city. So that's an example for urban scale monitoring. And they then, using these different infrastructures, they came up with emission estimates for the city. And here is kind of a model-based inversion posterior. Here is a more mass balance method based on aircraft observations, for instance. And this is the bottom-up estimate from the Hestia, which is basically the same as the Vulcan in inventory, or very similar at least. And you see that overall, there's a very good agreement between these different estimates within 7%. So that's maybe the level of accuracy you can expect with a very nice measurement infrastructure for a relatively simple situation as in Indianapolis. So next, I would like to explain a little bit what kind of observation approaches are available to monitor emissions in a city. And there's actually a lot of different options currently being tested also within the ICOS Cities project. So here, this nice schematic shows a little bit different options. So one is tall towers that are located primarily outside of the city. And you try to place always one tower upstream of the main wind flow direction and the other one downstream. So one should measure a background, whereas the other side should measure the background plus the CO2 or methane that has been emitted by the city. You can do this also with ground-based total column measurements. That is 0.3 here. That is, these are these orange boxes here. So they look into the sun and measure the total amount of CO2 along this path line. So the vertical column of CO2, and you can measure also upstream and downstream of the city. Other options are to have roof and street level networks. These are these many orange points here. So you distribute the sensor network over the city, but complement this also with measurements around the city to have a nice background quantification. And then another important method is eddy covariance towers. That's number 4 here. So in this example, there are 3 different eddy flux towers. So they don't measure concentrations directly, but they rather measure concentration fluctuations. And the covariance of these fluctuations with vertical winds gives information on emissions. So this method can directly quantify emissions, but only for a certain footprint around the measurement stations. So that's difficult to cover a whole city, but for a city district, this can work very nicely. And finally, satellite observations can observe a whole city. So far, we think that satellites can only measure emissions from large emitting sources. So larger cities, it will be much harder for smaller cities because the signal is relatively small. And finally, you could also fly with an aircraft around the city multiple times and see upstream and downstream concentrations. So when it comes to modeling, so how do you get from these observations to actually emissions? There are basically 2 different methods to do that. One I call mass balance method, and the other one inverse modeling. So I've placed some formula. Don't be scared. I will not go into the details. But basically, when you do a mass balance, you want to measure upstream. So here we see a source here that's, I think, a landfill, and we have a main wind direction. So you measure upwind of the source and downwind to measure the plume. And now if you measure the concentration in a surface downstream of the plume, and you also measure the wind perpendicular to that surface, then you have the flux of that species perpendicular to the surface. And if you integrate it over the whole surface, you get the total flux, which is equivalent to the emission source, at least for non-reactive species. So that's one method. That's, for instance, when you have these towers upwind and downwind, you can try to apply mass balance methods, or with aircraft flying around the source. The other method is inverse modeling, where you basically use an atmospheric transport model that simulates the transport of air from emission sources to receptor locations. So receptor locations would be our observation sites. And then you try to find those emissions which best explain the atmospheric observations, using the atmospheric model to produce the link between emissions and observations. So this H here, that's basically the atmospheric model. The X is the emissions. So the model transports the emissions to the observation sites, and then we can compare with the observations Y. And here that's a so-called cost function that we try to minimize. So we've tried to find that solution X, those emissions that minimize this cost function, that minimize the difference from the observations, but also using a priori information. Here's an example how this matrix H may look like, because this is a sensitivity of an observation site to upstream emissions. And this changes with time, with the flow. And here's just a map for many observations points the sensitivity to emissions over Europe at a given point in time. So that's the two options we have. And now when we think again of our observation systems, so which quantification method basically works best for which observation? So I mentioned these upstream and downstream methods with in situ measurements and total column measurements. For these, you can try to apply mass balance methods. So just measuring the flux of your greenhouse gas outside, downwind and out of the city. And satellite observations basically can be used in a similar way. So you can apply mass balance considerations when you have a network of sensors within the city and around the city. Basically, that concept doesn't work, but you need to use inverse modeling. So you need a transport model that simulates the transport through the city. But such inverse modeling can actually also be applied to all these other methods. So you can also incorporate observations from towers, from total column observations in such an inverse modeling framework. Whereas I think, mass balance can only be applied to these here, but not to the last one. And finally, there's the eddy-flux towers, which really is separate method. This is a direct emission measurement method. But as I mentioned before, you can not easily cover a whole city. You can cover certain regions, but then this provides very useful information. So I'd like to add some general considerations. So all these techniques depend on measurements of concentration gradients and differences between different locations. So it's very essential that you have a good calibration of your measurements within the network, that you can really compare the concentrations measured at one point with the concentration measured at another point, because your method really relies on the differences between these, let's say, background concentrations and downstream or in-city concentrations. So the most important gradient is between the background and locations within or downwind of the city. So a good estimation of the background, what is the concentration of your greenhouse gases before they reach the city, so outside of the city, a good background estimation is essential. Then the station selection needs to be carefully planned. You should analyze the dominant wind patterns so that you know where is upstream and where is typically downstream. And the stations should also be representative for a larger area. So they should not be too strongly influenced by local sources. So if you would like to have a measurement station, if you would move it 100, 200 meters away, you would still measure the same thing because it's not locally influenced. Otherwise, it's really hard to use such a measurement if it's locally influenced. It's also another consideration is that cities themselves influence the meteorology because they produce heat, they store heat, absorb heat from the sun and so on. So that complicates things, and the atmospheric model needs to account for that. But also if you do, let's say, mass balance considerations, this can complicate things. The nice thing with remote sensing of total columns is that to measure the total column, so you're less sensitive to boundary layer dynamics. You're not so much interested in how high is your atmospheric boundary layer. Is it 500 meters or 1,000 meter high? Because you always measure the total column irrespective of its mixing in the boundary layer. So that's one big advantage of this method. And another point is cities are usually not flat and isolated. So unlike Indianapolis, And the measurement network that is set up needs to account for this complexity. And I'm just showing here I'm slowly coming to the end. I'm showing here the example of what we have set up in the city of Zurich. So here we have decided to set up a network of sensors combining street level cheap sensors, so low-cost sensors, which we can put on lamp poles, with more accurate and more expensive sensors. We call these mid-cost sensors, which are also calibrated on rooftops. We've placed these on rooftops. And we also operate a number of high-precision instruments at background stations surrounding the city, but also inside the city. We also have actually one site where we have an eddy-flux tower. We have a tall building, more than 100 meter tall, on which we have placed an eddy-flux measurement site. We also have flask samples to do so-called relaxed eddy-flux covariance measurements. And we also have a wind LiDAR because we want to understand the flow within the city. In addition to this wind LiDAR, we also have a lot of wind sensors on rooftops in the city to have a better handle on the wind. In terms of the modeling system, in Zurich, we operate two model systems, one at very high resolution, building resolving model at 10 meter resolution. We need that because we want to compare simulations with the street level sensors. And for that, you need to be able to resolve street canyons with a model. We have a coarser model, ICON that runs at about 500 meter resolution. So obviously this model is unable to simulate gradients between a street canyon and a park around it. But we want to use the rooftop measurements that measure larger gradients across the city and background concentration stations. So we have currently set up these systems, but unfortunately, I'm not yet able to show you results. But with this system here, we would like to assimilate both these sensors, but especially also the street level sensors. And with the second coarser model, we can make use of the rooftop sensors. And finally, I'd like to mention that there's a lot of activity in many places, and there's a big science team that has gathered together and drafted a nice report, which is called this ICOS Urban Greenhouse Gas Emission Observation and Monitoring Best Practice Research Practices. So that's a report where you can find a lot of more information about the advantages and different disadvantages of different strategies. And to summarize, spatially explicit bottom-up inventories form a basis for urban emission monitoring. These inventories are uncertain, and top-down methods can provide independent verification. Emission monitoring with observations and top-down methods allows tracking progress towards emission reduction targets. As I've shown, there are a lot of different options how to observe and to model these emissions. Within ICOS Cities, we try different methods and different modeling strategies in order to come up with clear recommendations, what kind of method works best, maybe also for which type of city, because at the moment, we don't know really which method works best and which should be prioritized. That's a little bit why we apply many different methods at the moment. So ICOS Cities hopefully will give answers to which methods work best and which should maybe be given up. In addition, when you're setting up observation infrastructure, it's not only scientific considerations, so which measurement at what place would work best, but it's also a lot of logistic and financial aspects. It can be very expensive to set up a tall tower. It can be very difficult to find a good place above roofs to locate, to place a measurement station. So that's as important as scientific considerations. And I've mentioned these ICOS guidelines, developing best practice guidelines. And this is a rolling document. We hope that to adjust and update these documents when new information from scientific studies become available. And with that, I'd like to thank you for your attention, and also my colleagues at Empa and the whole ICOS Cities team. With that, I think I can stop my sharing.
Thank you so much, Dominik, for your talk. That was brilliant to give this overview. And so I hope everybody is on board here. I don't think we have a question right now, but if you do have one, please do put this in the chat and we will pick this up after the last talk. And as Dominik said, emissions are very important. So we will have a deep dive now, kind of into emission inventories from, I think, Jeroen starts and then Ingrid, or maybe the other way around. But please, Jeroen, the stage is yours.
Yes, I will start with the first part of this presentation, but
sorry,
no problem.
Sorry about that.
No problem. Yeah, first of all, thanks Dominik for this very nice introduction. Gave a very nice overview of urban emission monitoring and the role that emissions play in this. So we will go a little bit more detail into these urban emission inventories and what they're being used for. So if you can go to the next slide. A first very basic question, what is an urban emission inventory and why do we need it? Well, basically an emission inventory is nothing more than a database containing information on emissions for specific pollutants or greenhouse gases that occur within a specific region and time frame. And often these are separated into different sources like road transport or the industry. But it can take very many different forms depending on the goal that you have with this inventory. And I've shown here two examples. So at the bottom right, you see a very simple picture illustrating the contribution of different sectors to the total carbon footprint of Paris in 2014. This kind of information can give guidance to climate mitigation policy. So you can see immediately which sectors contribute a lot to this to the total carbon emissions within a city, which offers guidance to climate mitigation. However, this kind of information doesn't include spatial separation, which is needed, for example, for air quality modeling and exposure assessment. So the figure at the bottom left shows a very different type of inventory. In this case, it's for the city of Zurich, where you see emissions occurring with on specific road lengths that differ in intensity. And this kind of information you can put into an air quality model. So you can combine information on levels of air pollution with the presence of people to assess exposure to air pollutants. So these are just two examples, but you can think of many different ways to compile an inventory. And basically, I want to go through some choices that you can make when compiling such an inventory. Can you go to the next slide, please? So first thing you can think of is, what is my starting point? You can start, for example, with the country level emissions that are being reported, well, especially for European countries. They report emissions of greenhouse gases and air pollutants annually. And you can use that as a basis for your inventory. So for example, if you know the total emissions for a country for road transport, and you know the total amount of vehicle kilometers that are used to calculate these emissions, you can combine that with local information on vehicle kilometers in your city to get an estimate of the emissions that occurred within the city boundaries. The other option is to start with local data. So for example, the figure shown here, it basically shows the natural gas consumption of a power plant in Munich. And with this information, you can calculate the emissions coming from this specific power plant within the city boundaries. This type of information is more dynamic and considers the local conditions. Next slide, please. So based on that, you might want to add spatial information as well. And this connects to the starting point. So if you start with country level emissions, one way to add spatial information is with downscaling. And this is something that we also do building a European inventory, which is shown here at the top left. It basically shows CO2 emissions at a 1 kilometer resolution for part of Europe, but it's consistent with the national reported emissions. So we start with the CO2 emissions reported, for example, by Germany or the Netherlands, and we distribute it spatially using all kinds of proxy data like information on road network or population. And you can do that also for cities, either starting from the national total or from a European inventory like the one shown here. And we've tested this for the city of Munich. And we used data shown here at the right, just some examples of land cover maps and population density to downscale these 1 kilometer emissions to even a finer resolution, in this case 100 meter resolution. The advantage of this approach is that you do not need to know beforehand the total amount of emissions within the city boundaries because it's already constrained, in this case, by the inventory. Next slide. The second option is when you start with this local data, it often already includes spatial and temporal information. So here again, an example for the city of Munich, where they have many traffic count stations. And they combine this information with traffic models to calculate emissions from road transport at a specific location at a specific point in time. So with this kind of data, you already have spatial and temporal information included from the start. So there's no need to downscale it any further. Of course, this means a lot of data processing is needed. Which is much more challenging than starting from the national scale and then apply downscaling. But it does include local conditions, so it's more dynamic and probably contains more local information. Next slide. So the one final choice that you can make is the scoping of your inventory. So the examples that I've shown here contain only scope 1 emissions, and these are emissions that occur within the city boundaries. And this is often the type of information that we put into models, whether these are for air pollution or for greenhouse gas modeling, but you basically want to know emissions that occurred at a certain location. However, for example, for carbon footprinting, you also want to include scope 2 and scope 3 emissions. And these are emissions that occur outside of the city boundaries, for example, related to power generation or the consumption of goods that are being produced elsewhere. But if you want to get an overview of the impacts that a city has on climate change, then all of this should be included in the end. So this is another important consideration that's related to the goal that you have. So some final points on the challenges of working with these inventories. I've looked a little bit into guidelines for urban greenhouse gas inventories, and it's not very easy to find anything about this. So I found this greenhouse gas protocol for cities, which just gives some guidance to building an urban inventory for greenhouse gases. But there's not something available for air pollutants. And this leads to a lot of inconsistency between city inventories. For example, in the choice of which sectors are included, the scope of these sectors, but also sector definitions. You have different options for that as well. And sometimes only the most important sectors are included, and sometimes all sectors are included. And this makes it very difficult to compare inventories with each other, but also with the national inventory. And now Jeroen will go a little bit in more detail on that part. So how do you compare these city inventories and what can we learn from that?
Yes, thank you. Sorry, yeah. So thank you, Ingrid. Yeah, let me. Somebody.
I think Alex needs to go on mute.
Yeah, hopefully it will be okay now. So thank you, Ingrid, for the nice introduction and what you just mentioned, because now I would like to take over and continue a little bit more diving into the topic. So I will talk mostly about the air pollution, which is a side topic a little bit from the greenhouse gases, but on the other hand, we're talking very much about the same issues. And that's why it's really nice that we bring the communities together here to talk about this. Because cities are a hotspot for air pollution, like for climate change. There's just a lot of people, a lot of activities there. So we all know that. And we have emerging concerns about, on the air pollution side, about exposure to air pollutants. We have the traditional ones like NOx and PM2.5, but we have also new emerging pollutants like ultrafine particles. What is their impact on our human health? We all live in the cities, what's happening there? So that's something that we are particularly interested in, and that's also why, from the air pollution perspective and the perspective of the Urbans project, where I'm showing some results from today, we are interested in looking at that. So first of all, how to monitor urban air emissions, and here the scope issue that Ingrid just presented is very important. It may sound obvious to most of us that we are looking at really scope 1 emissions, meaning the emissions that actually really are occurring within the city boundaries, but it's not obvious to everyone. So it's something to be aware of when we talk about emissions. And one of the things that we are particularly looking at is the downscaling approach that Ingrid just introduced. So we start from European-wide or national or some other emission inventories that are there, established, based, for instance, on the official national inventories, like Ingrid just introduced. So you can take them as a starting point, a downscale to constrain your city level emissions. Though we have the official inventories, but we don't have that for all pollutants. If we talk about ultrafine particles, for instance, we don't have it yet. So at the same time, when we're developing ways to look at emissions in urban areas, we also look at emissions of new pollutants. And I wanted to show a picture about ultrafine particle emissions here and the main sources contributing to that. And next to that, the main sources of PM2.5. And just to make the point here that looking at different pollutants, which seem to be both are particles, it's probably the same sources. No, it's not always the same sources. It's important to realize that, and we should look at all these things individually. So transport is a particularly important source when it comes to ultrafine particles, more than industry or small combustion activities like for mass-based PM2.5. So that's something we developed there, and at the same time we provide the spatial distribution at the European scale. So Ingrid just introduced that as well. So we get maps like this, which show basically the emissions over the whole of Europe, which can be really useful into regional assessment of air quality. But as a next step, we really want to zoom into these cities, because this is based on the European approach. And of course, with everything like that, when you zoom in more and more, you get more uncertainties with such approaches. So it's important that we get a more handle on that. So therefore, we developed a downscaling tool. So this is basically similar to the what was just presented also by Ingrid, which is the application. In this case, we go from the 6 kilometer resolution of the European inventory to around 1 kilometer resolution. We use various proxy data sets, as we call them, to do that. So we take the 6 kilometer data sets. We take data sets like the land cover from the Kuenen database. We have OpenStreetMap for road transport networks. We have EPRTR, which describes point source emissions. And we can use that to basically disaggregate from the 6 by 6 kilometer cells to a 1 by 1 kilometer resolution, as is shown on this graph. This was developed a couple of years ago, and it's documented in a paper, which is here on the slide. And we are now actually working further to improve the downscaling methodology to make it fit better. But at the same time, by improving that, we're looking at that and see how it works. So I want to show you a couple of examples. For this, in this downscaling, here are two examples. So there's first one is the NOx emissions from public power sector in Helsinki, and the second one is PM2.5 from residential combustion emissions over Athens. So just two kind of random examples over Europe. You can see for Helsinki, you see first you see specific dots which represent point source emissions. So already in a European database, they are identified in specific locations where specifically the power plants are located with a source strength. But there are power plants that are basically below the threshold for emission reporting. They are just very small, so they don't occur in your point source database. So those are distributed more as diffuse sources, just to make up the difference between the point source total and the national total. And you can see that they are spread here in a higher resolution. For PM2.5 from residential combustion, on the other hand, all these emissions are diffuse because they are basically emissions from heating your houses. And they are distributed using, for instance, population density in specific regions. So you see that in specific areas, you get higher emissions than others. So this way you try to detail the European-wide inventory to a high resolution to make it fit for local assessment and local modeling activities. We're also doing that now for the ultrafine particles in the example that I showed. So this is the case of Barcelona in this case. So here you see again these 6 kilometer resolution blobs being downscaled to higher resolution for a specific case. So it's nice that we can do that, but it's more important what can we actually do with that and how can we bring things forward. And that's why, therefore, we need to take into account, take stock of these bottom-up emission inventories, because by comparing these downscaling approach to the bottom-up inventories that are developed by cities, and we know this is difficult and produces challenges, but we have some specific bottom-up inventories. And with these comparisons, we can really learn how our methods, our downscaling method and our bottom-up inventory, what's the advantage of both and how can we bring them together. So the downscaling approach is shown here on the left, and the bottom-up inventory on the right-hand side. This is the example of NOx emissions from road transport. And you see that there's relatively good agreement in most of the locations. However, you see some larger discrepancies. If you look at specific areas like here in the south of Barcelona, there's a port area which is not well represented. And there are more things when you zoom in, but I'll not go into all the details. Another example, again, the PM2.5 from the residential and commercial combustion. So this is mainly heating. And here you see much more differences. At least they are more recognizable, because you see in the bottom-up inventory, you see basically everything is more or less yellowish, whereas in the downscaled version, you still have some higher emissions. And this is most likely due to the way that emissions from wood combustion are spatially distributed in the downscaled approach. So because apparently in the local situation of Barcelona, in the local inventory, there is no or hardly any wood consumption within the city boundaries, whereas in the European approach, which is then downscaled, there is some wood consumption there, which leads to this difference that we see here. And if we summarize those findings for the case of Barcelona, you see here the two comparisons for road transport and for residential combustion again. For different pollutants, you see that for road transport, it seems that the downscaled version, which is the red one here on the slide, seems to underestimate compared to the local bottom-up inventory. Whereas if you look at the residential, it seems to be kind of the opposite. And there are some specific reasons for that. For instance, for PM, we know that the European emissions that are building on the official reported emissions do not include resuspension, which explains probably part of this difference. At the other side, in the wood combustion, in the residential combustion, we know that wood combustion distribution is an issue here. But the thing is, when you would add them up and you would look at the total for Barcelona, and these are the two main contributing sources of PM mass emissions, you would probably see, oh, those are quite similar if you would add them up, the two pictures here for PM10 or PM2.5. But the source sector contribution is really different. So it's important to do these kind of comparisons also at specific sector level to make sure that you understand really if they are similar or if they are different and how that is, what that is related to basically. So those are a few small examples that I wanted to show, and now show a few conclusions. Urban emission inventories, important to realize that they can serve a wide range of purposes, which determines the requirements with regard to the resolution, the scope, etc. So it's important to keep the back of our mind that they can be different because of that. And what we would like to show, what we've shown here, is that downscaling is a useful methodology to compile high-resolution urban emission inventories at various spatial scales. It can be from 1 kilometer, but also down to 100 meters or something. And this is especially useful when no local inventory is available, because these local inventories are not everywhere, and they may be different also from one city to another. But also the downscaling comes with uncertainties. Right? Generic, national, or European inventories may be relatively consistent. Also, they have their issues, but I will not go into the details of that now. But obviously, they, in the way that they spatially distribute and disaggregate emissions, some local circumstances may be missed. And the way forward with this is really to compare these different approaches for emission inventories, because only then we can really learn for which sources they are different, for which areas, in total emissions, but also spatial patterns, and understanding what these differences are and how they are, what they are caused by, is really driving improvements, because only then we can learn. And that's also where the top-down approach that Dominik presented earlier is really useful, because this can again support our understanding of emissions in cities. And last, it's important to realize, as I mentioned, that different pollutants or gases may behave differently for different sectors. So if you look at one specific comparison, it may be completely different for another sector or another gas, another pollutant. So that's important to realize when we work with emissions. So with that, I would like to close, and thank you very much for your attention.
Thank you very much, Jeroen and Ingrid. That was fantastic, your talk. We have a question in the chat. And if anybody else has a question, please put it in the chat or just raise your hand. From Alex, can you list advantages of combining air quality and greenhouse gases information in validating bottom-up inventories? I guess this goes to TNO.
Yeah, I think I mean, they are building, these inventories are typically, most of the emissions are caused by the same processes. So by definition, there's an advantage in combining this information. If we do this, that's also why it's great that we are here together from the different communities, because when we have measurements from CO2, for instance, that point towards that a certain source may be underestimated in the city, then it likely also means something for the air quality emissions and vice versa. So there's definitely advantages when we combine these things, also combine observations that we have to really learn about what are the driving activities in the city. And the nice thing about CO2 is that it's it's very much not related to technology, the emission. It's really the amount of fuel that's used in the city is what's driving the CO2 emission. And while for air quality, you have the technology factor that plays a big role. So if you have depending on the type of appliance that you have and abatement, your emission may be very, very different. So in that sense, it also helps, again, to understand this. I hope that answers it more or less.
And Dominik, would you like to pose your question directly to Jeroen?
Well, yeah, but what I mentioned in the chat is that some cities have emission inventories, but not necessarily in a gridded format. So providing a way of spatially distributing these emissions, and I think that goes a long way towards the downscaling method that you apply. Could that be an approach that the city, if it has an inventory, it contacts you and you tell them how to spatially map?
Yes, I mean, that's definitely a possibility. You know, it's a way to constrain the city boundary emissions, and you could use the existing the downscaled emission that you maybe base on the European approach, and then scale it so that the city total matches the city the own city inventory. In the RAI Urbans project, I should say that we also are dealing with different cities. We have, I think, 9 or 10 cities from the top of my head where we make such comparisons. And there are some cities where we actually have this issue that we have a city inventory, but we don't have the spatially explicit information. And we haven't really, we are still going to deal with that, but this is something, yeah. And already the comparing just the total from the bottom up city inventory versus the downscaled inventory is a useful way to understand. You can look at more than just the spatial distribution. Already the total, comparing the totals helps to understand.